Okay, hi there. Um, so before we dive into neurons or shading, I want to take a quick look at what we might call classical engineering. So before machine learning came along, a massively simplified view of all of our jobs might look like this. First, we humans attempt to understand a problem and come up with a solution. Then we describe the solution to a computer through coding. And finally, if we're successful, the computer can do it and we're all really happy. Unfortunately, though, there are times when this process doesn't really work. Sometimes we might not be able to figure out the solution, or we might even be able to prove mathematically that there is no solution to something. Or what's most important to us for this course is we might know the solution and we might be able to do the math, but it's simply too expensive to do in real time. So is there another way? Well, yes, as I'm sure some already know and maybe some aren't so familiar with, there is a way, and we call it optimization. So with this approach, rather than attempt to solve a problem, we come up with a really big set of potential inputs and corresponding desired outputs. We feed those inputs into some highly parameterizable mathematical model, and that generates us some outputs. And we calculate how wrong our outputs are. And if we're close enough, we can say, problem solved, and we've got something we can use. If not, we have to tweak those parameters that control the model, and then we try again. And hopefully with the right numerical techniques and enough iterations of this process, we end up with a model that's usable in production. So before we dive into any examples, I want to run over the tools we're going to be using for most of this course. First up is Slang. This is a really powerful new shading language that's now managed by the Kronos group. It's highly cross-platform. It allows you to write shaders in one language that can be used with D3D and Vulkan and Metal and Gouda. It supports a lot of really nice modern language features. One of my favorites is generics, but there's many more. And really important for us on this course is that it supports autodiff. So as a language, it can do calculus, so we don't have to. And alongside Slang, we've got SlangPy. So this is a Python-focused library that also supports C++ and sits on top of Slang. It's a really full-featured graphics API, fairly low level, gives you access to textures and samplers and compute buffers and so on. Again, highly cross-platform, supports D3D12, Vulkan, CUDA, and Metal. And on top of the lower level stuff, it provides what we call a functional API. So SlangPy allows you to directly call Slang methods from Python, and it does all the work of generating compute kernels and boilerplate that would typically come along with GPU coding. So on to our first problem. For our first SlangPy program, what we're going to look at is mipmaps. So mipmaps, as I'm sure many are aware already, are used in graphics for two purposes. They both reduce aliasing and improve memory coherency when sampling textures on objects in the distance. The basic idea is that if we're generating two neighboring pixels on screen, we'd like to be sampling two neighboring pixels in a texture, regardless of how distant an object is. But when generating these mipmaps, we find color maps like albedo, for example, downsample really well just using a simple box filter. And that's because if you take, say, a black pixel next to a white pixel and merge the two into a grey pixel, it makes sense to our human eyes. However, when we start dealing with maps that really represent geometry, such as a normal or a displacement map, these naive filtering mechanisms work very poorly. And that's because you can't simply average out geometry in the same way you can colors. If you take a peak next to a trough, you would downsample to a flat surface, and simply incorrect. You've gone from something that was bumpy to something that's flat. And what we see when we try and use this naive approach is highlighted on the right-hand side here. Even in this stationary image, you can see we've got a lot of sort of white speckly noise and uneven surfaces on the rocks, which are specular highlights that have been introduced by an incorrect normal. So we're going to go through a few steps for this example. First up, we're going to start by writing a SlangPy program to render a really beautiful PBR material like this one here. Then we'll look at generating lower resolution bitmaps, and we'll use them to render the lower resolution material. And what we'll be able to observe is these specular artifacts. Then we'll try a different approach to rendering our low-res material using supersampling, and hopefully we'll observe many fewer artifacts. And finally, we'll aim to generate a texture that shows the difference between the two for each pixel. So it shows us how wrong we are, which we'll label the loss texture. So on to some programming. We're starting out with slang code here. We're going to create a material parameter structure which has an albedo map, a normal map, and a roughness map. So here we're storing them as tensors or 2D buffers, but really this is no different to textures. They're just 2D grids of numbers. And alongside these parameters, we're going to provide a set of accessors, a function to get the albedo at a given point, another to get the normal at a given point, and one more function to get the roughness at a given point. So here is the heart of our Slang program. It's nice and simple. It's a render function, which takes those material parameters, along with a light direction and a view direction. Feeds the inputs into a BRDF, which I'm not going to dive into here. Ultimately, it's just a function that takes material information, a light and a view direction, and gives us back a color. For those interested, this one's a Disney diffuse with specular lobes, so it's not too complex, but most people wouldn't want to write it more than once. And finally, we're just going to take that color, scale it by light intensity, and return the result. So switching over to Python now, this is our whole SlangPy program on one slide. It starts with creating a window and loading our Slang module. And we're going to load up our textures. And inside our main loop, we'll allocate a tensor to receive some results. Then we'll pass the material along with a fixed light and view direction directly to the Slang render function. And SlangPy is smart enough to know here that since we're giving it some 2D grids of pixels, the albedo, the normal, and roughness, and we're asking for a 2D grid of pixels back, it should generate a kernel that runs the render function once per pixel. So finally, once we've got our output, we'll render it to screen. So what we get when we run that simple program is a really pretty rendering of our high resolution 2K cobblestones. And if we look closely, you can really see that beautiful specular detail on the surface of the stones, which is created by the normal map, where the light is interacting with these sort of bumpy, detailed peaks and troughs. But we're not dealing with nice, beautiful 2K textures. We're dealing with bitmaps. So the first thing we've got to do is downsample these high resolution textures to get our bitmap levels. So on the left-hand side, we've got a Python function called downsample. This contains a for loop in which each iteration we're going to call a Slang function. And the Slang function on the right-hand side simply returns the average of 4 neighboring pixels. So in other words, it's a box filter. So combined, our downsampler with one step will take us from 2K to 1K. Another step will take us from 1K to 512 and so on. So this is what we can use to generate a bitmap level. To render it, we're going to make a really tiny modification to the Python program. Every frame now, we're going to downsample those textures twice and we'll feed them to the render function. So now we're doing exactly as we were before, but we're feeding it 3 512 by 512 maps, and we're going to get a 512 by 512 render out. And here's our result. From a distance, you might be able to spot some kind of noisy pixels, but when we zoom in, it becomes really very obvious. All these sort of white speckly details have appeared, and the rocks have developed some pretty kind of strange specular patterns. All this is because in downsampling the normal map, we just invented new surfaces that didn't really exist at a higher resolution. So it looks wrong, but it is actually performant. We're doing one sample of each map per pixel, and we're running this PBR function once per pixel. What we'd really like to do is retain this same performance, but end up with something a lot prettier. So in that previous example, we saw what happened when we downsampled the inputs, the albedo, the normal, and roughness maps to our model, the BRDF. To try and get something nicer, we're instead going to try running the process at full resolution, and we'll just downsample the output instead. So here we're generating the full 2K output we had originally, then we're downsampling it to 512. In other words, what we're doing is we're taking multiple samples per pixel, which we call supersampling. And I think even zoomed out, you get a sense of a much more stable, less noisy image here. If we zoom right in, we can see all that kind of white speckly noise has gone. We've lost the really beautiful high resolution details because they're now sub-pixel, but the surfaces of the stones are still scattering light fairly uniformly, and our low resolution image is actually representative of the high resolution one. Unfortunately, to do this, we've had to take 16 samples of the high res, albedo, normal, and roughness map per pixel. Then we've run our expensive PBR function 16 times, and we've averaged the result. So this just isn't practical to do in real time, but it does represent what we might call an ideal output. If we could somehow create perfect bitmaps, this is what we'd want to see when we then rendered them. So before we move on, let's just compare the two. You can see that much noisier bitmap image on the right-hand side with these odd patterns on the stones where we've simply invented geometry that just shouldn't exist. So we know we've got something good on the left and something bad on the right. The next step is just to evaluate how wrong we are. To do so, we need to calculate the error using what we call the loss function. So we'll start with slang on the left-hand side. This function looks a lot like the earlier render function. It takes as input a reference color from the supersampled material, the low resolution material, a light direction, and a view direction. We generate the low res color by feeding the low res material into the render function, and we calculate the difference between it and the reference. We then square the result, and that gives us our squared error. The Python side is again very similar to the earlier render process. We're now calling loss instead of render, feeding it the low res material, the reference color, and the light and view direction. So when we render that in the center here, we've got a loss texture. Each pixel represents how wrong the output from the low res material is. A dark pixel represents a low loss, where we generated the correct output, and a bright pixel is a high loss, where the output was very wrong. And as you can probably see, we've got a really noisy loss texture here with lots of very bright pixels. So in other words, there's a lot of work to do. However, on the bright side, we've got the first step to making things better. We know how wrong we are, and we know that if we can find inputs that make that loss texture darker, we will have generated a better bitmap. If we can end up with that loss texture black, we'll have generated a perfect bitmap. So I'm going to hand over to Benedict now to show how we can use optimization to do exactly that.